Okay. Are you ready? I feel like you need that, like, I don't know, that pep talk. I don't have it, so consider yourself pepped for this last half. So, you know how I said Unit 9 is the big one, right? Right? What percentage of the AP exam is from this unit? 25%. Okay? Of the entire exam. 25% of the entire BC exam is from this chapter 9. Okay? Of that 25%, a few questions come from the first half that we just did. The majority of them come from what we're going to do right now. Okay? There is always a free response that is completely devoted to sequence and series. Sometimes there's a full one and then parts of other ones. One year there was a full one and 2 parts of other ones. So, I mean, it was huge. But there's always a full free response, and it always comes from this second half that we're getting ready to talk about. And you'll see as we go through today, there's a lot of writing to it, but the points are easy to pick up. Okay, so if you're an algebra person who's willing to do the writing, this can be your thing. All right. So, find the equation of the tangent line. What? That's not new. Equation of the tangent line to f of x equals sine at x equals 0. Okay, what 2 things do we need for a tangent line? A point and a slope, right? Okay, so let's find our point. I know x equals 0. I can find the y value by plugging it in. So our ordered pair is 0, 0. Check. What else do I need for a tangent line? Slope, and the slope comes from the derivative. Okay, so let's take the derivative, and then what do I need to do with that derivative? Plug in the 0, right? So the derivative at 0, what's the cosine of 0 again? 1. So we're ready to write our tangent line, right? Right? Y minus 0 equals 1 times x minus 0. Basically, y equals x, yes? Okay. Use the tangent line above to approximate, we've done this before, to approximate the value of the curve, meaning the sine of x curve, at 0.2, 0.5, and at 1. So doesn't that just mean plug in plug in the 0.2 for x? Well, if I plug it into the tangent line, don't I just get 0.2? Because if y equals x, does that make sense? If I plug 0.2 in for x, where's my, my pointer? There it is. You realize how much I loved my pointer. If I plug 0.2 in for x, what do I get for y? 0.2. So we're saying we're estimating the actual curve to be 0.2. We know the actual curve is not 0.2 because we didn't plug it into the sine of x, we plugged it into the tangent line, right? Okay, and if I plug in 0.5, I'm estimating it to be 0.5. And if I plug in 1, I'm estimating the tangent to be, the sine of x to be 1, right? Okay, then it says, compare the tangent line approximation to the actual value. Okay, calculator people. So what is the sine of 0.2 on your calculator? Everybody's in radian mode, right? What is the sine of 0.2? Anybody getting 0.198? Okay, so our approximation using the tangent line was 0.2, but the actual value is 0.198. That's pretty darn close, don't you think? Okay, if I plug in 0.5 into my sine of x, what do I get? 0.479. Anybody get that? That's still pretty close, yes? Okay, and if I plug in a 1, the sine of 1 is 0.841. Okay, so I used the tangent line to approximate the value, and then I found the actual value, and I'm trying to compare how close they are. Do you notice anything about these? Is my approximation getting better or getting worse as I move towards 1? It's getting worse, right? Where was my tangent line centered? At x equals 0. So the closer I am to the point of tangency, the better it is, correct? Does that make sense? Okay. Note, a tangent line is a first degree polynomial. First degree, what do you mean? What's a first degree polynomial? Don't say tangent line. What do I mean when I say first degree polynomial? What's the degree of a polynomial? The exponent, right? Right? And isn't a tangent line a line? It's x to the first. I mean, it's trivial, but we could call it a first degree polynomial. What would be a second degree polynomial? A parabola, and so on, right? Okay. So I just want to show you a picture. This is the red is my sine graph, and then the blue is my tangent line that I drew at x equals 0. And notice I zoomed in a little bit. These are the points that we plugged in, the 0.2, the 0.5, and the 1, okay? It's actually on the curve. Right here, it's like the tangent line and the curve are almost the exact same thing. Do you see that when I zoom in? But as I move away from 0, up here, I can start to see a teeny tiny little difference, right, in the tangent line and the curve. And the further I move away, I can see even more of a difference in the tangent line and the curve. So that's why you can kind of see that's why our estimate was getting worse as we moved away from 0. Okay? Well, let's try something. Calculator. Here's what I want you to do. On your calculator for y1 on the graph screen, I want you to put in sine of x. Don't hit graph yet. Sine of x. And then on y2, I want you to put in x minus x cubed over what? What's 3 factorial? 3 times 2 times 1. 6. So if you want, you can put in x cubed over 6. But before you hit graph, everybody got both equations in? So that we're all looking at the same thing, how about we use the Zoom 6 window? So press Zoom 6. Okay. What do you notice? Do you see how it's following the sine curve pretty closely? Right? I've got my sine curve. Do you see this was my polynomial? Look how far it's the same as the sine curve. Remember, my tangent line was only the same, like really close. What if I were to plug in a 1? Just look at your graph. Wouldn't x equals 1 be right here? At x equals 1, aren't they virtually the same thing? Do you see how it's much better than when I just used the tangent line? Right with me? So if I use a cubic, it's a much better approximation than a tangent line. Do you think y2 above would give a better approximation? We just talked through that. Okay, compare the equation of y2 to the equation of the tangent line. Remember the equation of the tangent line was y equals x to the first? It was this part. But then I added on randomly this minus x cubed over 3 factorial. Do you see any kind of a pattern? I went from a first degree to a third degree. If I wanted to, could I write this as like x to the first over 1 factorial? Isn't x the same as x to the first? And isn't 1 factorial just 1? So if I think of this as x to the first over 1 factorial, and then the next one was x cubed over 3 factorial, if I were to keep going, what do you think the next one would be? X to the what? 4th or 5th? Right? Because I had 1 was odd, 3 was odd. X to the 5th over what? 5 factorial. Do you think it would be a plus or a minus? This one's positive, this one's negative. Would you speculate that the next one would be a positive? Try that. Just go to your y2 and add on there x to the 5th over 5 factorial. Hey, you guys, we're going to start getting higher and higher. Do you all know where factorial is? You can either do a search or factorial. You can press math. I have to remember it. You get your number in, so put in your 5. And then for factorial, you can press math. And then you go to the PROB, probability, and it's down on number 4. Math, probability, number 4. And when you hit graph on that one, is it any better? Hey, look. Doesn't that one extend out along the sine curve even further? Do you see that? What would the next one be? Plus or minus? Minus x to the 7th over 7 factorial. See how close that one is. Whoa. That takes it all the way out to like almost to 5-ish, doesn't it? Where it follows the curve. So the higher the degree polynomial we use, the more accurate it remains to be the same as the sine graph. Yes? Everybody seeing what I'm putting out there? Okay? So in the olden days, back in the AB times, all we might be able to approximate with is a little old tangent line, which might be good, if you're really, really close to the point. But what Unit 9 does is it expands it so that we don't just use lines, we use squares and cubes and to the 5th, and oh my gosh, what if we just keep raising the power infinitely? Could I have a polynomial like to the nth degree that would actually match the sine curve exactly? That's where we're going. Okay? So, polynomial functions can be used to approximate other elementary functions, such as sine x, e to the x, natural log of x, and so on. Okay? All right, here comes the writing. You ready? We already did the thinking and the look at where we're going. Here comes the writing. If a function, f, has n derivatives, we just have to say that. Okay, all the derivatives exist. They're polynomials, so we don't have to worry about it. All the derivatives exist at a particular point. Then the polynomial, notice I'm labeling it P sub n. That stands for polynomial of nth degree. We might say find the 4th degree polynomial. We would say P sub 4. If I want a 3rd degree polynomial, we would say P sub 3. Okay? So the generic formula to write a polynomial that matches a particular curve, okay, it's going to look ugly at first. We start with f of c plus f prime of c times x minus c. And at first you're like, oh my goodness, what a pain. Isn't that just equation of a line? What does f prime of c stand for? Isn't that just the slope? Right? In fact, isn't that kind of like a y minus y1? Isn't this the y value at c? So you could say, hey, if this is my y minus y1 equals m times the quantity x minus, remember that? Isn't that just the equation of a line? That's like your tangent line. I mean, yeah, I moved the y1 over, but that's just the tangent line. Oh, well, that's not a great polynomial. That's just a 1st degree. What if I want to keep it going? Here's the pattern. What? I know you said writing. Here's the pattern. If I want to extend it to higher degrees, the pattern is that you have the next derivative over the next factorial. I don't know if this is helpful to you, but isn't this f prime of c, isn't that kind of like the first derivative over 1 factorial? Even though we don't write it, this is kind of like the 0 derivative, meaning it's not a derivative. You with me? What would you speculate the next one would be? The third derivative over 3 factorial times the parenthesis to the third. Okay, I want you to see the pattern here. And if I really want to extend it out to n, we're going to be writing a lot of these in this section. So the problems we do are not going to be usually one little line. They're going to be like 6 to 8 lines. But then we'll start learning shortcuts and that kind of stuff.
And it's always addition?
It's always addition unless the value of your derivative is negative, where that would bring in a minus. Yeah. Now, this right here, whenever we get a derivative so high, we don't, like the 10th derivative, we don't write 10 little slashy marks. Once you get beyond the third derivative, we just write the number, like f to the 4. That's not a 4 exponent, that means 4th derivative. Or f, with a superscript of 5, that means 5th derivative. And you might say, well, how do I know if it's derivative or exponent? The context of the problem. If you're doing it in this, it's the derivative. Okay? So that's our pattern. This is called the nth degree Taylor polynomial. Okay? It's called a Taylor polynomial for f at c. And it's named after some guy that we don't care about. All right. If c equals 0, meaning if it's centered at 0, remember when I did the tangent line to the sine function? It was tangent at 0. So if they tell us that we're centered at 0, then it's called down at the bottom, that bottom blank, it's called the Maclaurin polynomial. I'll let you fill in up above in a minute. So in other words, when we say if it's centered at 0, that means we're saying if c is 0. So instead of saying f of c, it would be f of 0. Instead of saying f prime of c, it would be f prime of 0. You follow me? This is just the special name if it's centered at 0. It happens pretty often, and they'll use the word Maclaurin to let you know, hey, this one's centered at 0. And when they're centered at 0, you're going to jump up and down and be excited because it's just nicer to plug in 0, don't you think, than other things? So the one we did a minute ago on the graph, we were looking at the Maclaurin polynomial for the sine function. We looked at the first degree of the tangent line, then we looked at the third degree, and then we looked at the 5th degree, and so on. What do you think, Joanna? You don't see this kind of fun stuff at Rice. That's not true. You probably will. Everybody with me? I try not to make sure I don't go too fast when I'm just clicking and you guys are writing. Everybody good? Ready to move along? All right. So here we go. Let's do it. I thought, you know what? If I just click these up there, they're going to be like, hey, so I'm going to do the work with you. Okay? I want to find the Maclaurin polynomial. What does that mean? Centered at 0. I want to find the Maclaurin polynomial of degree 6. So I'm going to go out to the... If it's degree 6, I'm going out to what derivative? Because this is the 6th derivative times the x to the 6th. Bear with me. Of cosine. So what I like to do is I'll just start listing out my derivatives. So if my f is cosine, what's my derivative? Negative sine. And I'm just going to kind of keep going on my derivatives and then we'll finish. What's my second derivative? Negative cosine. And what's my third derivative? positive sign, and my fourth derivative, what? Cosine. Hey, aren't I back to where I started? Right? So the fifth derivative is negative sine, and the sixth derivative is negative cosine. Okay. In order to fill in my polynomial, I need the derivative at 0, don't I? Okay, so here's my column for at 0. What's the cosine of 0? 1. Sine of 0? 0. Negative cosine of 0? Negative 1. Sine of 0? Cosine of 0? Negative sine of 0? Negative cosine of 0. Okay? So now I'm ready to fill in. Here we go. I'm going to use good notation. So the 6th degree polynomial, this is my notation for 6th degree polynomial. Okay, so we start at the top. Don't we need our f of 0, right, which is just 1. And then normally I go to my first derivative, so I'm going to say plus, but what is my first derivative? 0. So I'm going to write this one here so you can see that I did, and then we'll start skipping them. So it's like my first derivative times x to the first. And it's kind of over 1 factorial, even though we don't really write it since it's just a 1, right? Just so we can kind of see the pattern. Everybody with me? Okay, so let's keep going. And then, Kelly, here's what we were saying. I would say plus the second derivative, but because I see the second derivative is negative 1, I'm going to say minus, there's my second derivative. Right with me? And then I need x what? Squared over 2 factorial. So now that we see that the third derivative is 0, can I leave that one off? And then I'll go to my fourth derivative, which is positive 1. Remember, this was a fourth, so it's x to the fourth over what? 4 factorial. Everybody with me? I'm just filling in the pattern. The fifth is 0. So the next one is negative 1. So my sixth degree is minus 1 x to the sixth over 6 factorial. So there's my 6th degree Taylor polynomial. I'm done. I've done the first part they said. Everybody okay? Good? It says, then use that polynomial to approximate the value of cosine of 0.1. So basically, I'm trying to plug in 0.1 everywhere I see an x. So it's going to be 1 minus 0.1 squared over 2 plus 0.1 to the fourth over 24 minus 0.1 to the sixth over 720. And we know that because we talked about it last time. Remember we said 4 factorial was 24 and 5 factorial was 120 and 6 factorial was 720. By the way, we'll use these a lot. You'll start to remember up to like 6. So calculator, you do the calculator work. Calculator. Will they really ask us to do this? Yes, sometimes. Sometimes. Be interesting if we all get the same answer or not. It's always humorous to me how 10 people can plug in the same thing and get a different answer. Do we have agreement? 4 decimal places. Point 9. Did I hear 9? 0.9. 9. 0. right? I'm just curious, how accurate, this is my estimate based on the polynomial, right? And we were approximating the value of cosine of x at 0.1. What is the cosine of 0.1? Isn't it like virtually the same thing?
It is the same.
Well, for a long time. Probably if you go out to a lot of decimal places, it might start to change, but well, for as many decimal places as your calculator will do. Okay, so you see what we're doing, right? We're using polynomials to estimate curves. All right, ready for the next one? Let's try this. And by the way, I talked about how this is all over. In free response, it is what we just did right there could very well be part A of your free response. Very likely. Okay? Next example. Taylor polynomial, does that mean it's centered at 0? No, it would say Maclaurin, of degree 6 for natural log, but where is this one centered? At 1. All right, so we need 6 derivatives of starting with natural log of x. All right. First derivative, 1 over x. Second derivative, negative 1 over x squared. Third derivative, can you picture it without having to rewrite a bunch of junk? If you think of this as x to the negative 2, if you think of this as, you're going to spend forever doing these if that's the case. If you think of this as x to the negative 2, when you bring down the negative 2, wouldn't it become positive 2? But when you have x to the negative 3, I'll do that for you guys. Just so Joanna doesn't crawl under the table. There you go. So Joanna, since I helped you out, you help me out. What's the fourth derivative?
Okay. Negative 6x
To the negative what?
2.
What?
4.
4?
Yeah.
Not integral, we're doing derivative.
Yeah.
Everybody good? Keep going. Negative or positive? 24x to the what? Negative 5. And then what? Negative 120x to the negative 6. Okay, where is this one centered? At what? At 1. So that means I'm going to plug in a 1. It's centered at 1, so the natural log of 1 is 0. Derivative at 1 is 1. And then what? Negative 1. And then what? 2. 1 to any power is 1, correct? So then we just have negative 6, 24, negative 120. Hey, do those numbers look familiar at all? 6, 24, 120? Because weren't we just multiplying by the next number every time? Right, that's what we were doing? So you're going to see some simplifying here in a minute. Okay, so my 6th degree polynomial is, start at the top, 0. No, you don't need to write it. For me, I tend to write it so I remember that was my first one, and now I go to my x to the first kind of thing. Okay, so first derivative is 1. And I don't just write x. Remember, if it's centered at 1, I have to write x minus c. So it would be x minus 1.
Do you not have to do the f of c at the very front?
That's this one right here.
Okay.
Right here. This was my f of 1,
Okay.
and this is my f prime of 1.
Okay, that makes sense.
Everybody with me? Fill it in? Okay, and then my second derivative is negative 1. And since it's the second derivative, I know it's going to be the x minus 1 squared. Everybody okay with the x minus 1 versus the x? Because it's centered at 1, I need x minus 1. The last one was centered at 0, so it was x minus 0. All over what, you guys? 2 factorial. Then I go to the third derivative. So positive 2 x minus 1 to the third over 3 factorial. Then I go to the fourth, minus 6 x minus 1 to the fourth over what? 4 factorial. And then plus 24 x minus 1 to the fifth over 5 factorial. Minus 120 x minus 1 to the sixth over 6 factorial. And because we can, let's simplify. All right. So this is just x minus 1 minus 2 factorial is just 2, right? So I'll just leave it as x minus 1 squared over 2 plus, what is 3 factorial? 6. So 2 over 6 is 1/3. So x minus 1 cubed over 3. Am I seeing a pattern here? Minus, what is 4 factorial? 24. So 6 over 24 is 4th. You want to trust the pattern on the next one? If we follow the pattern, what do you think the next one's going to be? X minus 1 to the fifth over 5 minus x minus 1 to the sixth over 6. It says use it to approximate natural log of 1.1. We're not going to do that. We want to practice the pattern. Everybody okay? See what I mean? It's like tedious work, but it's like follow the pattern, fill in the derivatives, fill in the formula. Everybody okay? Are we okay? So writing out that much work would be like a part A on a free response. Okay? What part A? The good news is the part B and C, it's not as much work. But the bad news is it's more thinking. Sorry, it's a trade-off. All right, how would they wouldn't make you do that much work on a multiple choice. How would multiple choice look like, you ask? Well, I'm glad you asked. Look at this one. Okay. Suppose that g is a function that has continuous derivatives. They give me g of 2, they give me the derivative at 2, they give me the second derivative 2. Basically, they're giving me all the numbers I need. Do you see that? And then it says, write the Taylor polynomial of degree what? Degree 3 for g centered at 2. Well, if I want degree 3, don't I need the 3 derivatives? But I don't need to know the actual derivative. I just need to know the derivative at 2, don't I? So don't they give me what I need? Okay, you got the formula right there in front of you, right? So we want polynomial of degree 3. We're not going to have to do any work. They've given me all the stuff. I'm just going to fill in. What goes first? Isn't it the original function at what, g of 2? So what's g of 2? 3. So there's my first term. And then I need the first derivative. What's the first derivative? -4. But where is this centered? At 2. So what goes in my parentheses? X minus 2. Everybody with me? They did all the work. I'm just filling in. And then I need the second derivative. What's the second derivative? Then the second derivative 7, but now it's going to be x minus 2 what? Squared over 2 factorial. I went ahead and just said 2 factorial is 2. Is that okay? If you want to write 2 factorial, you can. And then I need the third derivative, which is -5, x minus 2 cubed. Again, I went ahead and said over 6 because if it's a multiple choice, I think they would change it. But do you see how on multiple choice they give you everything? You just have to know the pattern.
I
No. That one would definitely, in fact, much of the time they're not. When it's just that kind of thing.
So it won't be like plug in 0.1.
Oh no, that would be calculator. Yeah. Everybody doing okay? How else might you see this one? Okay. Write a third degree Maclaurin polynomial. Maclaurin what? Centered at 0. Okay. Third degree Maclaurin polynomial for e to the x. And use it, okay, forget the use it, we'll come back to that. Third degree Maclaurin for e to the x. You want to try it all by your little self? So do your 3 derivatives for e to the x. You know, go slow because I don't want you to hurt yourself. F of x, f prime. Everybody done with your 3 derivatives? And we are centered, oh, it said Maclaurin, so centered at 0. So what are all of our numbers? 1. Okay, so set up your polynomial. And then see if we agree on the polynomial. Do we agree on the polynomial? All good? All right. Now, did you label yours as the little p sub 3? Okay. Now, I went ahead and wrote this because this is our polynomial that's estimating e to the x, right? I'm not saying you have to write that, but this is estimating e to the x. Look at the rest of the question. It says use it, meaning use the polynomial, since you know that we're thinking of that as being equivalent to e to the x, to find this limit. So in other words, we're going to do this limit, but in place of e to the x, we're going to put in that polynomial. Okay? So in place of e to the x, put in that polynomial. So you're going to have the limit of polynomial minus 1 over 2x. Everybody see what I'm doing here? And why would I do this? Because they told me to. Otherwise, I probably wouldn't. I'd probably do the limit a different way. Just doing it because they told me to. Anything gonna cancel out? The ones cancel. So I've just got, and by the way, I know you have fractions and fractions. Who cares right now, right? Don't worry about the fractions. Once you simplify, then what do? I substitute in 0 for x. If I put in a 0 for x, then what do I end up with? Don't I just get 1/2? 1 plus 0 minus 0 all over 2? Questions?
Where did the 1 come from?
Oh. What did
And also, isn't it 2x on the bottom too?
I factored out an x. If I factor out an x to cancel that x, you see what I'm saying?
Oh.
Sorry, if I substitute right here, I'm going to have 0 over 0, so I factored out an x on the top, so it would cancel with this x. That leaves me with the 1 plus 1/2 x plus 1/6 x squared. Sorry, everybody okay with that? Huh. Should that be a free response or a multiple choice? Really, part A would be like find the third degree polynomial for e to the x, and part B would be use it to evaluate the limit. That wouldn't be bad for an A and a B, would it? That's not bad, right? Yes.
Why is it negative 1/6?
I don't know. That's a good question. Seems like it should be plus, doesn't it? You're right. Good catch, Rania. Good job. Okay. Here's a good one. Channel your inner algebra 2. You ready? Okay. Given that the second degree polynomial is a plus bx plus cx squared. So we don't know what a, b, and c are, but it's just this second degree polynomial. We good? Let's see. It's the second degree Taylor polynomial for f about x equals 0. What can you say about the signs of a, b, and c if this is the graph of f? So would a, b, and c be positive or negative if this is the graph of f? All right. So based on that a plus bx plus c, isn't a the f of 0 term if you think about our formula? Right? Because isn't that first constant the f of 0? And what is b? Isn't b the f prime of 0? Everybody see what I'm talking about if I pull it out of that formula? And what is c? Be careful. It's not just f double prime of 0, but it's f double prime of 0 over 2 factorial, isn't it? Because isn't over 2 factorial part of your constant? Does everybody see what I'm talking about there? Is everybody okay? All right. So based on this, look at the graph. What is f of 0? Positive or negative? Doesn't that mean the y value at 0? Doesn't f of 0 mean the y value at 0? So is the y value at 0 positive or negative? Or is it too easy? You're afraid to say positive? Everybody okay with that? All right. All they asked me for was the signs. They didn't ask me what number. They just said what sign. What about the derivative at 0? Positive or negative? Positive because my graph is increasing. There you go. And what about, does the over 2 factorial change the positive or negative at all? No. So the second derivative, positive or negative? Negative. I like that one. That's a good one. Okay? Now, do you need to jump up and down for a minute? Do you need a snack? There's snacks in those bags back there. There's pretzels and goldfish and little fruity things and something else. There might be some little plates in there if you need little plates. Did you see the little plates in there?
Sour Patch cookies. Thank you so much, okay, what? Last time. I got it.
I couldn't find the normal little fruit chews. This was like, I don't know, like something berry or I don't know. The normal is like the blue box and not the purple box. I don't like change it up in my boxes. All right, so everybody's all awake and good to go now, right? Okay. So you can like chew and write at the same time. Okay? All right, here we go. So that was 9.7, the polynomial idea. Okay? Now we're going to blow that polynomial wide open because a polynomial ends, right? 6th degree ends at x to the 6th. 10th degree ends at x to the 10th. But what if I want it more accurate than that? What if I want it to go on forever? If it goes on forever, it's not a polynomial anymore because polynomials end. But series go on forever, don't they? So here's where we turn it into series. And by the way, the 9.7, we talk about polynomials. The whole rest of the chapter now, we talk about series. They end in ... Same concept, but it's like the infinite polynomial that ... Okay? All right, here we go. So the good news about these is that here's where we get some shortcuts. That's why I like to get to this point today, so you can start to see the shortcuts. Okay. In general, Taylor polynomials can be a good approximation. They can be a good approximation for a function. It smells all fruity in here now. It can be a good approximation for a function. All right. Someone after my own heart. Animal crackers, they're just a good go-to, aren't they?
They're so good.
Okay. Taylor polynomials can be a good approximation for a function near a particular value of x, right? Because we know the farther you go away from x, the less accurate they are. Okay. The higher the degree of the Taylor polynomial, the larger the interval over which it fits the function closely. Right? We saw that on our graph, remember? The tangent line was kind of close for a little bit, and then we got to the cubic and it was better, and then we got to the fifth and it was better, and so on. Okay? A Taylor series, circle, highlight, underline. So now we're not talking polynomial, we're moving into the next part, we're talking about a series. Okay? A Taylor series can be thought of as an infinite Taylor polynomial. So a Taylor series just extends it forever. So we call it an infinite Taylor polynomial for f of x at x equals c. So you still center it somewhere. You're still approximating a particular function. We just go on forever. Okay? You understand the difference between Taylor polynomial and Taylor series? Really, the difference is ... And for real, on a free response, if they say find the polynomial, you have to have a final term. If they say find the series, you have to end in ... And if you don't, they think that you're writing a polynomial and you lose the point. Okay? And you don't want to put a ... on a polynomial because then they think you mean the series. Got the idea? Okay. So a Taylor series centered at x equals c, well, it's the exact same formula. You're doing the exact same thing. You're just going on forever, right? Oh. Can you remember the formula without looking back? F of c plus, see if you can remember without looking back. F of c plus f prime of c times x minus c. Oh, thank you, Jesus. So you went out to the f to the nth derivative, right, over n factorial x minus c, but isn't that how we ended the polynomial? So what do I need at the end? Yeah, plus ... But because we know how to write a series in sigma notation, we can write the Taylor series in sigma notation. So we would say the sum, as n goes from 0 to infinity, of the nth derivative at c over n factorial. Basically, you just rewrite that general term in the series. Okay? And so we know that that sigma represents the going on forever sum. SUM. I bet you all can fill in the next blank if you haven't already. If c equals 0 is a series, if c equals 0, the series is called what kind? A Maclaurin series. So the Maclaurin polynomial, Maclaurin series, both mean centered at 0. It is not, I'm sorry. But I tried to give you lots of space. Would you have preferred me do it landscape?
No, it's fine.
Yeah.
Landscape is gross.
I know, but, okay. Find a Taylor series for f of x equals e to the 5x centered at 2. We got this. Ready? Do they need to tell me what degree? No, because we're going on forever. Ready? That's why you need to get a snack. We're going on forever. Give the first 4 non-zero terms. So if I only want the first 4 terms, I really only need to go to the 4th derivative, right? Does that make sense? All right. So f of x is e to the 5x. So the derivative is what? 5e to the 5x, and the second derivative is 25e to the 5x. I already see a pattern, and the third derivative is, instead of 125, is it okay if I just write 5 cubed? It's kind of like, by noticing that, I'm already starting to see the pattern. Is everybody okay? E to the 5x. And the fourth derivative is what? Don't say 625, even though I know you know it. 5 to the 4th, e to the 5x. Okay, centered at what? 2. So if I plug in a 2, I have e to the 10th, and 5e to the 10th, and 5 squared e to the 10th, 5 cubed, e to the 10th, and 5 to the 4th, e to the 10th. So again, yeah, it's monotonous because it's the same thing, but hey, thank you, Lord, I'll take it, right? Could be way worse. All right, so I'm going to say, here's how I'm going to write my series. And I'm not going to call it p because it's not a polynomial. I'm going to say e to the 5x, because this is the series for e, okay, is, so f of 2 was e to the 10th plus the first derivative, 5e to the 10th times what? X minus 2, because it's centered at 2. And then the second derivative is 5 squared e to the 10th, x minus 2 squared over what? 2 factorial. Hey, how many non-zero terms do I have right now? 3. So I really only need one more, right? Yeah. Because that first one counts. And so I need my, what am I on? Third derivative? Third derivative, 5 cubed, x minus 2 cubed, 3 factorial. So here's how we write our notation. You ready? It says the first 4 non-zero terms, check, and then it says, and the general term. So we're going to write plus, dot, dot, dot. Okay? So the general term, what's the pattern? Doesn't every single one of them have a 5 to some power? Don't we have, like, look right here, 5 to the 0, 5 to the first, 5 to the second, 5 to the third? You with me? Oh, thank you. Okay? And doesn't every single term have an e to the 10th? See how I'm trying to write the pattern of what everything has?
You have to put like a plus in front of that.
You can, it doesn't matter. Okay? And then I have x minus 2 to the n all over what? N factorial. So that's what we call the general term. But that's still not the end. I mean, there's still like this dot, dot, dot. If I wanted to write it in sigma notation, basically I just put the sigma in front of that general term. It's like the general term is the sigma notation. So this could be known as the series as n goes from what? 0 to infinity of that stuff.
Are we allowed to skip to that step, or do you have to do that?
This one you could, like if you just wrote it right here, they would say, oh look, there's their general term.
Okay.
Yeah.
You know, right? Like, where's that?
No, you don't have to write that. Everybody doing okay? All right. First four in general term, check. Again, that could be an A, part A. All right. Here's first term, second term, third term, fourth term, general term. We wrote the series. We did all that. Okay. Here you go. You want some shortcuts? All right. Never again should you have to figure out the series for e to the x or sine x or cosine x. We are going to write them down. We're going to memorize them, and I promise you by the end of just today's homework, you will know them forever. Okay? So there are three special Maclaurin series that you must know. You have to know these. Almost everything we do comes back to these. Okay. E to the x. We did that. A couple problems ago, we developed the e to the x one. Basically, it came out to be 1. I'll let you write, and then we'll talk. How's what? Did you throw something at her? An animal cracker? Don't waste animal crackers that way. Okay, good. How do you feel about iced animal crackers? They are, but I could probably eat the whole bag if I did that. I have to stick with the non-iced. They're still good. That's like the iced animal crackers. That's like taking ice cream and dipping it in sugar. I do too. I do too.
That's our best selling cake.
Really?
Mm-hmm.
I do too.
We call it Crazy Zoo because we
Hey, can you guys write the sigma notation for e to the x? Write the sigma notation for e to the x. Right? Write the sigma notation. So for e's, it's nice because it's just right in a row, right? You start at 1, and then it's just x to the first, x to the second, x to the third, x to the fourth, and same factorial. So that's kind of easy to remember, don't you think? Do you remember when we first started and I showed you the sine one? What kind of powers of x did we have when we did the sine function? That first one that I showed you. Didn't we have the odd ones? Okay, so the sine one is just the odd powers. So you start with x to the first, and it's all of the odd powers. But notice that the sine one is alternating. Positive, negative, and so on. And you'll notice that in the general term, we put that -1 to the end because that's what shows us the alternating part. Remember how that's the idea for alternating, -1 to the end? Where in the heck did I get 2n plus 1? What's that about? That's how I make it always be an odd number, because n is an integer. As soon as you multiply it by 2, it's always even. So you can either add or subtract 1 so that it's always odd. So 2n plus 1, when you see that, you should just think odd number. Everybody okay? So can you write the sigma notation for that? Write the sigma notation?
So have we looked at a bunch of these in other series, not knowing that they
Yes. We didn't know the shortcuts because I wanted you to kind of see it. The first one where I showed you odd. And you may not remember, but we also did cosine. Do you remember what cosine turned out to be? Not odd, but even. Okay, so the cosine is even. So E has all the powers. E has all the power. It's exponential. Sine is just the odd ones. Cosine is the even ones. And so you have to know that cosine starts with the 1 because it's kind of like the zero term. Still alternating, so still -1 to the n, but this time we said x to the 2n because that's how you make it always be an even number. I need to be able to get to one example to show you how this is going to help you. So you have to know this, so you'll want to keep that handy when you're doing homework, okay? And you could write the sigma notation. Okay? So here's how those become powerful. You can use any of these manipulation techniques, okay? Used on the special series that we just mentioned to find any other series. So a lot of times other series will have an e to the x in it, or they'll have a sine in it, or they'll have a cosine in it, and you've already done the work for it. So basically you can substitute into the series. I'm going to have you write these down, then I'll show you the example. I'm trying to write these fast so I can show you the example, okay? You can multiply or divide the series by a constant or a variable. You can add or subtract two series. Like if you wanted to find the sine plus the cosine, you could just take the sine series plus the cosine series. You can, oh, there it is. Just when you thought it wasn't calculus, you can find the derivative or the integral of any series. Or you can recognize it as the sum of a geometric power series. Basically, this first part I'm getting ready to show you an example of. That second part is what we do tomorrow, just so you know. You don't need to write that part down. Okay, so I need to show you this one example and then you're going to be good. Ready? Here we go. Find the Maclaurin series for the sine of x squared. Hey, I know the sine of x, right? Right? So can you write it down without looking? Just don't write, the sigma, just write the terms. Remember, sine is the odd. It starts with x to the first minus x cubed. So don't worry about the sigma part. Just write it out to the general term part. Here's the beauty of it. Okay? But I don't want the sine of x. I want what? Sine of x squared. So that first thing that we wrote down before says you can substitute. So if I want the sine of x squared, basically I can just substitute an x squared in everywhere I see an x. So the work is already done. I'm just going to substitute in an x squared for every single x up in the previous line. Just put an x squared up, even in the general term, put an x squared in place of x. And so this way I don't have to do all of the individual derivatives. So once you get it substituted in, then maybe we can just, clean it up a little bit. All I'm doing is, raising my power to power. I just wanted to make sure we got to this part right here. Does everybody understand where I got this from? If I had x squared to the 2n plus 1, that you just multiply your exponents to get here. I'm going to narrow down the homework a little bit. I'll send y'all a message with that. Okay?
Do we still have a regular online quiz on Monday?
No, the one you're taking for this thing is the quiz, but it's due Sunday. Right, Jake? Sunday. Hey, good day, way to hang in there. It's a lot of stuff to start this part of it. See you guys. See ya. See you guys.
Here, are you giving me today? Can I do my test correction?
See ya. Yes, thank you. See ya.